good. Today, we're going to see the way of hacking hardware in embedded systems, mainly based on hardware. In order to place us into context, we usually call embedded system to any device with a specific usage that has a hardware-software integration which is not similar, which is not normal. For example, a fridge is an embedded system. 20 years ago, they didn't have any microprocessor, but nowadays, fridges do have processors. A TV can also be considered an embedded system with several microprocessors and so on. Currently, every electronic device could be considered an embedded system because any embedded system has microprocessors. 20 years ago, it was crazy to integrate microprocessors for bridges because the price would have been much higher. However, nowadays, the difference in price is not very significant. Probably these loudspeakers are also embedded systems because they have their own operating system, RAM, ROM, and so on. So most of the systems, security is based on the concept of security by obscurity. Since you don't know what there is inside, they are very difficult to attack. This is a principle that has been applied for forever, but regarding embedded system, this is quite relevant because a closed open source code is using security by security. In this case, let's think about our bridge. Who is going to attack our fridge? Well, maybe they want to attack an industrial fridge with over 200 kilos of meat inside. If I want the company to go into bankruptcy, to attract the clients to my company, then I could attack that embedded system. But I do not have any kind of code, any binary code. I only have some chips that I can see. There is a song by Leonard Cohen that I like, which says, there is a crack in everything. That's how the life gets in. So today we're going to see how to extract information from embedded systems. Embedded systems are not obscure by chance, but by necessity. The first need is plagiarism. If Samsung, for example, has different functions with a display in their fridge, probably they won't want LG or other companies to copy their functionality. Moreover, most embedded systems hadn't had any connection because they were not connected to any Wi-Fi before. When it rains a lot and the dam reaches a certain level, the doors, the gates are open without any human intervention. If I open the gate without any advice, without any warning, I can flood a whole village. And when this can, and this could cut the electricity grid for a whole region. The same happens with the fire extinction devices. If they do not work, some buildings can be burned and some human lives could be lost. So we need to think about critical structures. I like to talk about the electricity grid, but also about the network of dams, which are based on embedded systems, which are not very modern. If you go to any company in Spain, the automated systems to open the gates are 15 or 20 years old, because it is not a component which is replaced very frequently. Those devices are not connected and they do not require a complete modernization. However, it is difficult to think about a company which has Windows XP because it is 20 years old. It is very insecure. There are warnings from INCIBE that say delete Windows XP, but no one is telling the dam operator to change the system that controls the gates. So let's try first to see how we can extract information from these embedded devices. When we open it, we find this circuit board. If I open the TV, I will find a circuit board with several chips which contain the program, the software, the operating system, and so on. But it is not easy to extract that information. Manufacturers use this in order to hide the information. These techniques that I'm going to explain to you are usually used in the gaming company. I do not know if you are familiar with the MAME emulator. When we extract the information from a game, the game is going to have a high protection against plagiarism. All these techniques were developed to protect the information from games, but can be applied to these cases. The first thing which is difficult is to identify the security elements and to access them. This is a board from an arcade game, but it is very common to open it and to see that it has epoxy resin on it. Once it is solidified, this resin, it is extremely solid. So if I have this resin, I cannot access the chips, so I cannot access the information. There are several ways to delete this resin. So what can we do? Usually, I like to do it with hot air. This kind of epoxy resin can be broken over 400 degrees. So being patiently with a hot air gun, not want to strip paint with temperature regulator. It can be broken, and scratching it carefully, you can release the surface of the chips. Obviously, 400 degrees is very hot, so you need to be careful. But when you're working with systems that are covered with resin and you only have one, be extremely careful, because sometimes when you have several devices, one of them can be used as just to test, but if you just have only one, be careful. There are people who are more patient than I. If you submerge the epoxy resin in paint stripper for a couple of days, then the resin can be extracted quite easily. The same happens with butyl glycol, where you have to submerge the chip for only a day. But I'm not that patient. I do not have a whole day to wait. Another friend told me that he usually uses an ultrasound machine, but it is not very, I wouldn't recommend you to use this, because the ultrasounds can harm the internal connections. ultrasounds, and its vibration can break those connections, and the chip will be useless. Another common practice is that once we have withdrawn the epoxy resin, we don't know what there is below because they usually scratch the surface. We have seen this in devices with over 1,000 or even 2,000 chips. So there was a person scratching chips for many hours. But you can see where the chip is connected, what is the data bus, what is the bus of addresses, and so on. Most of chips have an electric identifier. If you put it into a programmer, it sends electrical signals to a high voltage, and the chip responds with an electric identifier. Not every chip does this. Not every chip has a unique identifier. Some of them share a family identifier. And in some other cases, there are some markings on the reverse of the chip, or the scratching was wrongly made. This is an example of a dongle key. Those of you who are young might not know this, but 20 years ago this was quite frequent. In this case, this is to protect against copies. There was a layer of resin. Once the resin was withdrawn, we saw a clock and a chip with the surface full of scratches. I don't know if you can see it here. Can you see there is a small symbol here, a small triangle? This symbol means manufacturer, which is an AMBEL chip. And so this was a mistake. He had scratched the chip surface and he had added resin, but he had forgotten to scratch this symbol. And here we have some markings that can be used to identify, to have the identifier. So we overcame the two protections by the manufacturer, resin and surface scratching. As you can see, these protections are very simple. They are not very sophisticated, but it really hinders the fact of identifying a device. Some people ask, why don't you use X-rays? Well, X-rays are not very useful. This is a device that is usually connected to TV. This is called gloss, in Spanish called petrol, and you use it instead of resin all over the chip. Here we knew that here the ROM was here because we were sure that it was a flash memory. However, we scanned it through X-ray. If you see resistors here, are these and these, so it doesn't give us any information. So X-rays are not very useful. They are only useful when we have a trap device. Sometimes below the resin we have a suicidal device which deletes all the information when it feels that it's going to be attacked. This is quite common, actually. NVRAM, it is a volatile RAM which is connected to a battery. So the content of the RAM is gonna be there and while it is connected to the battery. If the battery current is cut, the memory content is going to be broken. If you use 400 degrees of hot air, you're going to delete the content of the RAM. So in this case, it could be helpful to use X-rays. Besides, in Spain, the regulation on using X-rays is quite strict, which is good. Another way of hiding what is going on in an embedded system is that chips do not respond to any standard. In this case, here we have Ref 0034. This triangle says it is Apnel, a brand, and we have the same in Philips. This chip came from this dart machine at bars and pubs. We do not know its processors, we do not know anything. So how can we extract information from a chip we don't know? Another case which is quite frequent is when a manufacturer produces a huge amount of chips. For example, Hasbro, the owner of Play School and the owner of toy stores, produced video players that you probably don't remember because you are too young. In Spain, it was launched with a wonderful advertisement, and the advertising said, let's spend a day with a famous singer. In this case, this was especially produced for Hasbro. So there is no documentation or information on it. You may call the manufacturer saying you are Hasbro, but probably you won't speak the language and you won't be able to have the same device because it is specifically produced only for Hasbro. We have no idea what this is, but let's see later how to attack these difficult cases. Obviously, the thing about using a programmer to receive an electric identifier is not going to work on this device because the manufacturer produced this product specifically for Hasbro, so they would have included any identifier. So this makes it difficult for us to extract information. I have a hardware, I want to extract information. What can I do? Obviously, there is a kind of ROM of chip that if I pass it through a ROM reader, I can extract all the information. The programmer reads it and it reads it. But most of chips do have high protection systems. And the strategies depend on the kind of hardware. I usually tend to speak about dumping data from a chip with non-intrusive techniques, and the best way to extract information could be through trojans, although trojans are better used to extract information from a PC. Glitching is another technique. It is when there is a bad design on hardware and we can exploit this hardware in order to access information. We can also use brute force, but I think that only 4 or 5 components are subject to brute force and also decap. The decap of modern components is only made by governments, but old components can be accessed through decap techniques. As for Trojans, It is not just about writing a Trojan, it is about injecting it. Trojans are necessary in systems that are 100% embedded. It doesn't mean that the whole system is in the same board. The system is in a chip that has no external interaction. ROM is internal, RAM is internal, peripherals are internal. Since it doesn't have any external interaction, how can I inject the Trojan? Obviously, it is protected against read and against writing, and there is no external interaction. So the way of injecting this Trojan is to analyze it, because it might have one interaction with the external reality. Here we have Itachi, which was used in a game called Master Boy. The whole program was here. And this is a hack done by McDonald, sorry, and the ROM, in this case, the internal ROM, has text printing routine. So if I change the external ROM, which I can modify because it is external, if I change the text on the screen is going to change. The best thing is that the definition of characters is internal, and outside there are some pointers, some external pointers.
En la ROM externa, cuando quiero imprimir una A, no me va a poner A, me va a poner 0xFFF.
And this happens when printing some characters. Each character has a mapped address, and that address is going to be outside. When you start, there is a small diagnosis window that self-diagnoses, and it printed on the screen the whole set of characters. What did we do? We discovered that this small character printing routine didn't take any security analysis. So instead of sending a memory character, I send a memory address that corresponds to another area of the internal ROM. It is going to copy that part of the ROM in the memory of the video in order to print it on the screen. Obviously, on the screen you cannot find anything because it knows a map of bytes that corresponds to a character. So what we did was to modify the external pointers. We took the view RAM in order to transform it into an NV RAM. I think the volatile RAM was for kbits. From the internal ROM to the volatile video RAM, and then we copied those bits. Every 4 bits we tried to copy it, and in the end we managed to extract all the internal ROM because the manufacturer forgot to check if the addressing corresponded to a character and not to something that was outside the area of the memory. We had some complications because some of the characters were control characters, but in the end we could extract all the information, and it was a code, so we have the game completely extracted from the device. There is always a mistake by the manufacturer that can be exploited. I am going to set another example. This is one of the most secure chips. I had the chance to collaborate with the manufacturers. this in this project, I collaborated with Mr. Kierkegaard, who unfortunately passed away last week, and he was very young. Okay, so we have here this chip, and the whole content of Dallas is encrypted. It only admits encrypted information, and the encryption key is in a volatile memory connected to a battery. So any interaction will delete that memory, and in this case, it doesn't have any interaction with the outside. So, two problems. How can I inject a Trojan? And how can I execute the encryption key? I need the encryption key because my Trojan needs to have the same encryption key. The manufacturer was given a different encryption key to every device so that no one could know the encryption key. Here we have an adapter which is connected on the Dallas chip so that each of the wires are connected. But be careful because you cannot exert pressure. We also needed to modify, for example, to cut the reset line so that the main program, this is a Motorola, controlled by Dallas. So we didn't want the reset line to reset the chip. Once we had this, what we did, through brute force, we could find enough number of value pairs with encryption and non-encryption in order to know the encryption key. It is a bit difficult to explain because this is a very complex hack. Once we had extracted enough pairs of encrypted values and non-encrypted values, we can figure out the encryption key. And once we have the encryption key, we can take our Trojan, encrypt it with the same encryption key, and inject it in the modified hardware. In this case, we also connected it to an interface, a USB interface. I can see it right now. And we managed to extract the program of Dallas 5002. This is a very sophisticated Trojan. To write Trojans for embedded systems is not an easy task because it requires a lot of creativity, imagination, a lot of knowledge, and it is always, but however, it is always better than more intrusive systems. The next protection step is suicidal device. This one is the same one as the one before, the Dallas 5002, which is connected to a battery. Once the battery is lost, the encryption keys are lost. The idea is that chips control any physical intrusion and delete the whole content. On many occasions, chips are prepared not with a battery, but with something more complex. The electronic ID, if you apply a higher voltage over its threshold, deletes all the keys inside. And when you're going to use it, it will say volatile memory deleted, because it thinks the attacker is carrying out a glitching, which is one of the more frequent attacks. Okay, let's talk then about glitching. How can we use a malfunctioning of the hardware in order to invalidate anti-copy systems? This is a board by Super Nintendo, whose information we could extract thanks to this glitching technique. On many occasions, they have a testing device. You can play with voltages. There are some people who The glitching technique is not successful by chance. You cannot try to apply higher or lower voltage. You really need to understand the hardware in order to know how much voltage to use. I really like talking about glitches. A friend of mine recently broke the microcontroller SM590 by Nintendo, which is used in some robots, some absurd robots that were connected to NASA. Those robots had microprocessors. How could we extract its information? This is the sequence that my friend followed. If we feed electrically the chip and I apply some current through ACL R21 and R20, then through R13, from R13 to R10, it will start to publish its ROM. So the chip started to publish its code. How did this person know? Because my friend had an experience of 20 years and knew about this. Probably the manufacturer is only familiar with Nintendo architectures. However, my friend is familiar with several architectures and he is aware of the typical mistakes made by manufacturers, and that's how he managed to break this information. We're going to talk now about one of the most common protection systems. Most of chips have a protection bit. When this bit is established, the internal memory cannot be read. This works like this because sometimes we would like to reuse chips. So this protection bit enables me to change the content and to read what's written inside. On many occasions, that chip can be restored. So the chip can be passed from 0 to 1. I inject a program, I activate the protection bit, and then I cannot read it. But I want to reuse it, so then I can delete everything, including the bit of protection and also the content of it. On many occasions, it is not a bit that you can withdraw. It is like a fusible. Once the fusible is broken, you cannot read its content. So once I said I'm over and the fusible is broken, the chip is not going to be used anymore. So with this kind of chips, which are more frequent, are going to be our point of attack. Another example of glitching on which we based to attack the bit of protection. The Atmel 1889C2051 is the one that you can see on the screen. Do you remember the one with a resin layer and this surface which was scratched? It is this one. We started to think, what if this is a very classical weak by manufacturers? When I send a deletion order, it first deletes the bit of protection and then the content, because the microcontroller didn't have access to its own content due to the chip of the bit of protection. So if we stop the electricity current, so we send a deletion order, and in 10 microseconds we stop the current in order for it not to have enough time to delete the content. Obviously, 10 microseconds have been determined because we bought 50 of these devices and we were doing some tests. So with 10 microseconds, it was quite fair. And if you give it 11 microseconds, part of the content will be deleted. But
so the problem is that what we found out that Atmel, the manufacturer, solved this vulnerability in 1998. So it works just in series before 1998. Now we're looking for a vulnerability that works also in later series, because we have to break the ones of 1999. I've written here this blog spot from Arcade Hacker, which is a great hacker from Barcelona, so please take a look at it. Now I want to talk about the decapping, which is like the main technique. Decapping means removing the package of the chip until we can see the surface of the chip, until we can see that the image on screen. Once we have that, we can apply many different techniques. We can take micro pictures, microphotography. We're going to see that later. We can apply UV light in a selective way. We can apply laser. We can do many wonderful things. This is one of the techniques that is most useful for doing this hacking, and it is very simple because it just requires practice. It doesn't require you to be a genius. Main thing here is how to remove the substrate. Some people do it with like applying indirect hot, because this breaks the ceramics and the chip is preserved. So there are people who do this and then apply indirect hot and then put this into water, and this breaks the ceramics. But I don't know how they managed to make the chip work afterwards, because when I've tried, the chip is useless. This is a thermal decapping. You can do some thermal tests. These small lines are thermal test consequences that make the chip useless. These pictures are from a CapSoft group, which is great. But this thermal decapping requires a lot of practice. I don't usually recommend it because normally you are going to break chip after chip. You may see the content, but you are going to break the chip, and many of the techniques are going to require the chip to be completely preserved. So normally people use chemical decapping. There are some chemicals that attack ceramics and plastics, but not metals. Normally sulfur acid is used with concentration over 90%. So if you try this, of course you have to use masks, gloves, and you cannot do this inside a closed room. It seems obvious, but I must warn you that the fumes of sulfur gas are very harmful. This is, for example, a laboratory, and these are some chips that are already prepared in order to do this technique. Acid is quite useful. There are some debates regarding the type of acids that you can use depending on the cover of the chip. Also, there are people that are doing laser decapping. But this, if you have enough money, this is a great technique because the laser can erode the substrate, but it doesn't harm the metal. The metal is going to get warm, but it is not going to be broken. But of course, having a laser in order to do this decapping is expensive. No, not everybody can afford it. Well, I don't have a lot of time, but as you can imagine, at the end the chip will be completely preserved. And I don't know exactly who's this video from. In the groups in which I'm working, we cannot do this laser decapping because it is very expensive. One of the things that we are going to be able to do once we've done the decapping is identifying a chip. This is console and a dashboard, and we wanted to learn the processor that it was using. We couldn't do it. It was very difficult, and it was very hard to us to identify that. And in order to get ready for an attack, it's very important to have this information. So this is what we did. So something else that we can do is visual decapping. This is for very old devices. This is a ROM implant. This is contacting. This is not. This is contacting. So 1 1 0 0 0 1 1 0 1. This is what this contact and non-contact means. With a little bit of patience, you can have this information. There are visual artificial vision programs that are useful for that. You don't have to do this with a human eye. This is a giant JPG. Before we used to do it with the human eye, and we spread the work per squares, but with artificial vision now this can be done very easily and faster. I don't know if you can distinguish this here, but this is the memory area 0111000. These type of attacks are only going to work with very old chips, unless you have a nuclear microscope or something like that. This is not something that you can do out of your house, but with a Nikon microscope, you can already do decapping from chips from the 80s or 90s. This is a very good way of extracting information. Something else that is working very well is the UV mask. This is a chemical decapping. We've used a drop of acid that has destroyed the cover of the chip. But we have to be careful because UV light can delete or erase the content of the memory of the chips. In fact, there are some chips that you've probably seen that have a small mirror window. And this is done like that because these chips are rewritable, and in order to erase them, you have to put these chips under UV light for a period of time. But here what we've done is covering with nail polish all the content, and in order to protect the memory content. This requires a lot of practice in order especially when you are applying this nail polish. This works with every chip that may have a UV sensitive memory, MCU, PIC. This has a very common architecture from Intel, and here you can see, for example, that in this area that's not covered with the nail polish, we have the protection bit, and here we have the memory that we want to read afterwards. And after applying the nail polish, I can apply later the UV light. This is not complicated at all. Something which is more difficult is the use of laser. This is a laser of one of my colleagues. If you use a laser which is enough powerful, the laser can change the sense of a bit, the content of a bit. So this is the microscope that we are using to point the laser. The laser is going to point the protection area, but it may change the number of the bit. I can change the content on the bit from 0 to 1 by just using a laser, so we have to be careful with that. When we are talking about fuses, we can even when we are talking about fuses, we can do small weldings, and this is going to allow me to read the rest of the field, but these lasers are very expensive and very difficult to configure. In fact, this is the calibration system of one of these lasers. There are people that try to do glitching by applying lasers. As the light has ions, it can create some conductiveness in areas of the chip in which there shouldn't be any conductiveness. So anyway, it's very hard to find that area, that specific area of the chip. This requires having a deep knowledge on the chip. But I've always said that light glitching is not something that everybody can do because of the complexity of the process. Something else that we have, another technique, is micro-probing. But besides knowing the hardware, you need to have very good manual skills. These are some pictures from a chip from a game, I think, which had a very strong protection. I'm going to speed up a little bit, but part of the chip was cut. Here we have the processing part, memory, etc. And the memory was extracted in order for it to be read with an external device. And welding things to a chip at this level is very complex. I don't know how John and his team can do these things with practically a domestic laboratory. There are other hardware components, such as PLDs, that make this process even harder because they have an entry and exit. There are different types of PLDs, EPLDs, FGPA, probably FPGA are more popular right now. There are some devices that are called PAL crackers, and because as this is containing a formula inside, you can use brute force in order to try all types of exits and entries. And through different mathematical procedures, for example, if I have a lot of values for entries and exits, through an interpolation I can obtain the formula of these entries and exits, and this is the formula that the chip within these PLDs is using. But depending on the type of PLD, it can take years to obtain that information. I can use this type of techniques used with PLDs that have very simple algorithms inside. And well, finally, I just want to talk to you about the groups that are dealing with this type of processes. Sound Riddle, Caps Off, John McMaster, which is working for Capshot, Cole J, which is in charge of interpreting the inside of the chip. He knows exactly how each part of the chip interacts with other parts, if we are talking about analogical or digital parts. Team Europe is also doing great things regarding UV covers, UV masks. The Dumping Union is one of the groups with whom I'm working the most. Silicon Prawn is in charge of publishing contents of within chips. An Arcade Hacker is a great friend of mine and one of the best hackers of Barcelona. And just to finish my presentation, we've seen that we can obtain information from chips. And well, this is an advantage because it's going to give me all the information I need about a device. This is an access device that I obtained from a ministry here in Spain, and it has a ECU of 25. It is a very simple hardware. So I can transfer the ROM, and so what can I do? And I may be using this or any other type of similar devices. We can use MAME. MAME, well, this is the device, as you can see. You can do emulations of real programs, and we can use it through coding. I'm going to launch a small demonstration that I have here.
Aquí tengo, no, aquí no lo tengo porque no lo veis. Un segundo. Ahora sí. Aquí tengo el programa funcionando y este es el ensamblador del
So
NEC25.
this is the
Usa el juego de instrucciones del 186.
and the program, and I can, for example, with this, I can check if there are backdoors. I'm executing the code here. I can launch automatic testing. I can do anything I want in the hardware device. Before I couldn't launch automatic testings. I had to pay someone so that this person would be trying different numbers, 0000, and different other combinations, or different other combinations of introducing several commands at the same time. But this is a simulation of the execution of the program, and in fact, if I click here, see, or well, what I wanted to show you is that MAME, I mean, well, normally we try to register all the information in files because normally the pictures are more easily, may be lost more easily. But well, in the end, here you have just 20 lines of codes we've achieved to emulate a quite complex access control system. We can automatize entries, exits. We have everything there. We even have this controller of the LCD. I could even launch attacks towards LCD. For example, here we have V25 at 16 megahertz. So I can automatize all type of testings against our wonderful program. So it's true that this system, this access control system, may be interesting, because this can be tested in different ministers here. But I can try this in different power stations. I can control the fire alarms of a central or power plant. And finally, well, there are many people working in MAME, and well, this is an data acquisition system that was used connected to a cryogenization system that we got from a garbage. So I love the garbage of laboratories and that stuff. And well, this is used in remote data stations in which there is no signal. For example, in facilities in the middle of the mountain, they do not have a satellite connections. Once a month. So once a month, someone goes to extract the data from these devices. And we were wondering if we could introduce a virus in a meteorology emergency central station, because in the meteorology station, which is in the middle of the mountain, nobody's going to see me. I could go there and manipulate that device. Could try to infect the meteorology central station through the devices in the middle of the mountain. I would need to get to know that device, that remote device perfectly. But these are quite interesting attack factors. So systems that are embedded here may be very important. I mean, I've talked to you mainly about games because this is my field of work, but these are points of attack that are going to allow us to extract data and to audit at a more exhaustive level compared to what we could do without using these tools. So before finishing, I would like to thank INCIBE for having invited me to be here. I feel like home in this event, and thank you so much to all of you for attending my presentation. Thank you very much. Are there any questions? In the first system that you've explained, the Trojan closed system, you've said that the solution was connecting, that was changing the memory to a non-volatile memory. How does this process work? Well, it's a simple process. An RAM connected to a battery turns into a non-volatile RAM. So you need to look for a component that has the same characteristics. For example, if you can see the frequency at which it is working. In our case, we used an old plate that we used to hack another machine. And we could have used also this connected to a battery. The thing is that if you should be able to cut the power and to still preserve the content of the memory. So it's always going to be an RAM connected to a battery. Well, thank you so much to all of you.